Everything around you is made of matter. But what happens when you manipulate that matter at the scale of individual atoms, where the rules of physics no longer behave the way textbooks describe? That is the question nanotechnology is built on. This module examines what nanotechnology is, how materials behave at the nanoscale, where the technology is already being used, and why its governance, not just its science, demands serious attention. Nanotechnology is the deliberate manipulation of matter at the scale of 1 to 100 nanometers. 1 nanometer is 1/1000th of a meter. A strand of human hair is roughly 80,000 nanometers wide. At the nanoscale, you are working at the level of individual atoms and molecules. What makes this scale consequential is not just its smallness, it is what happens to matter there. Quantum mechanical effects become dominant. Surface area becomes enormous relative to volume. Properties like color, melting point, electrical conductivity, and chemical reactivity shift in ways that are both predictable enough to engineer and surprising enough to remain partially unknown in their long-term consequences. Key structures in this field: nanoparticles, carbon nanotubes, quantum dots, graphene, and lipid nanoparticles are not interchangeable. Each has its own physics, its own engineering profile, and its own risk signature. The conceptual origin of the field is Richard Feynman's 1959 lecture, "There's Plenty of Room at the Bottom," where he imagined building machines and storing data atom by atom. Norio Taniguchi gave the field its name in 1974. Today, the global nanotechnology market is projected to exceed $125 billion by 2030, with over 10,000 nano-enabled consumer products already on the market. The science moved fast. The governance has not kept pace. Consider gold. At human scale, it is yellow, chemically inert, and melts at just over 1,000 degrees Celsius. Reduce it to nanoparticles between 5 and 50 nanometers, and it is no longer yellow, it appears red, purple, or blue depending on particle size. Its melting point drops below 300 degrees. It becomes catalytically active. It can be functionalized to seek out and destroy cancer cells. This is not a different material. It is the same gold. The physics has simply shifted. Several mechanisms explain this. As particle size decreases, the ratio of surface area to volume increases sharply. More atoms are exposed and available for interaction. Quantum confinement alters electron behavior. Surface forces adhesion, van der Waals interactions begin to dominate over gravity. And optical properties change through plasmon resonance, which is why nanogold interacts with light differently from its bulk form. From an SDS standpoint, this is significant. It means that safety data gathered on bulk materials cannot simply be transferred to their nanoequivalents. A substance with a known toxicological profile at normal scale may behave entirely differently at the nanoscale, and existing regulatory frameworks were not built with that distinction in mind. Nanotechnology has a traceable intellectual genealogy, and understanding it matters because the discourse that surrounds a technology shapes how it is funded, regulated, and perceived often before the evidence is in. In 1959, Feynman posed the question theoretically. In 1974, Taniguchi gave it a name. In the 1980s, Eric Drexler elaborated a speculative but influential framework for molecular machines, while IBM researchers demonstrated that individual atoms could be imaged and repositioned using a scanning tunneling microscope. Speculation and experiment were converging. From the 2000s onward, nanotechnology moved from laboratory to marketplace. Carbon nanotubes entered structural composites. Quantum dots appeared in display technology. And in 2020, lipid nanoparticles became the delivery mechanism for COVID-19 mRNA vaccines, making nanotechnology simultaneously the most consequential and least publicly understood technology deployed in modern public health history. That gap between deployment and public understanding is itself an SDS problem. 6 nanoscale structures define most of what nanotechnology currently does in medicine, agriculture, energy, and electronics. Nanoparticles' spherical structures between 1 and 100 nanometers are the most widely used. Gold, silver, iron oxide, and silica nanoparticles have high surface reactivity and are used in drug delivery, imaging, catalysis, and sunscreen formulations. Carbon nanotubes are graphene sheets rolled into cylinders. They are stronger than steel at 1/6 the weight and are excellent electrical conductors properties that make them attractive for composites and future transistor designs, but also raise inhalation risk concerns because of their fibrous geometry. Quantum dots are semiconductor nanocrystals that emit specific colors of light based on their size A tunability that conventional dyes cannot match. They appear in QLED displays, solar cells, and biomedical imaging. Graphene, a single layer of carbon atoms in a hexagonal lattice, is the thinnest material ever characterized, 200 times stronger than steel, and a near-perfect conductor. It remains largely pre-commercial, but its application potential in filtration, flexible electronics, and energy storage is substantial. Lipid nanoparticles and liposomes are hollow lipid-based carriers designed to encapsulate and protect drugs or nucleic acids until they reach their target. Doxil, a liposomal chemotherapy drug, was approved in 1995. The Pfizer-BioNTech and Moderna COVID-19 vaccines use this same platform. Dendrimers are branched synthetic polymers with a tree-like structure. Their surface groups can be engineered to carry drugs, target specific cell types, or bind biological markers, making them versatile, but also structurally complex to manufacture and regulate. Nanotechnology is not a single application. It is a platform that reconfigures what is possible across multiple sectors simultaneously, which is precisely what makes its governance so complicated. In medicine, nanocarriers deliver chemotherapy, drugs directly to tumor cells, reducing the collateral toxicity that makes conventional chemotherapy so debilitating. The mRNA-LNP platform, validated during COVID-19, has opened the door to therapies for diseases that previously had no effective treatment. In diagnostics, nanosensors detect cancer biomarkers at concentrations orders of magnitude below what conventional assays can resolve. Quantum dot contrast agents enable real-time cellular imaging. Nanotechnology has improved the sensitivity of rapid diagnostic tests, including the COVID-19 lateral flow tests many of us used. In agriculture, nanofertilizers improve nitrogen uptake efficiency by 30 to 40%, reducing the runoff that drives coastal eutrophication. Nano-encapsulated pesticides reduce effective dose while maintaining efficacy. These are not marginal improvements in regions like Ilocos Norte, where paddy agriculture is intensive and Lingian Gulf is downstream. The implications are direct. In energy, perovskite and quantum dot solar cells are approaching efficiency thresholds that silicon alone cannot reach. Nano-enhanced batteries offer significantly higher energy density. These matter for the decarbonization agenda. In water treatment, carbon nanotube membranes filter viruses, heavy metals, and micropollutants at scales inaccessible to conventional filtration. Iron oxide nanoparticles remove arsenic from contaminated groundwater. Nanosilver coatings provide antibacterial function without chemical disinfectants. In electronics, the transistors inside your current smartphone already operate at dimensions of just a few nanometers. Without nanoscale engineering, modern computing as it exists would not be possible. Targeted drug delivery is worth examining in some detail, because it illustrates both the therapeutic precision that nanotechnology enables and the complexity of translating that precision into clinical practice. The mechanism works in 3 steps. A nanoparticle surface is functionalized antibodies or ligands are attached that recognize specific receptors overexpressed on cancer cells. The nanocarrier then circulates in the bloodstream, evades immune clearance through its size and surface chemistry, and accumulates preferentially in tumor tissue through the enhanced permeability and retention, effect a consequence of the abnormally leaky vasculature that tumors develop. Once inside the tumor microenvironment, the drug is released in response to a local trigger, a pH drop, an enzyme, or light activation. Healthy tissue is largely spared. Several nanomedicines are clinically approved and in regular use. Doxil liposomal doxorubicin reduced cardiac toxicity in ovarian cancer treatment and was approved by the FDA in 1995. Abraxane, approved in 2005, binds paclitaxel to albumin nanoparticles for use in breast, lung, and pancreatic cancers. Onpattro, approved in 2018, was the first RNA interference drug delivered via lipid nanoparticles. The COVID-19 mRNA vaccines, authorized in 2020, represent the most widely administered nanotechnology platform in history. The SDS point here is this. The same platform that delivered COVID-19 vaccines globally was, for decades before 2020, a niche pharmaceutical technology that received limited public attention and inconsistent regulatory scrutiny. Crisis accelerated adoption. Whether the governance infrastructure kept pace is a separate and open question. Agriculture is one of the fields where nanotechnology's practical implications are most immediate and where the gap between potential and evidence-based policy is most visible. Nanofertilizers urea coated with hydroxyapatite or polymer shells slow nitrogen release, improving uptake efficiency by 30 to 40%. The practical consequence is reduced nitrogen runoff into waterways. For farming communities whose drainage flows into Lingayen Gulf or Manila Bay, this matters directly. Eutrophication from agricultural runoff is not an abstract environmental concern, it degrades fisheries and coastal livelihoods. Nano-encapsulated pesticides extend active compound persistence on plant surfaces, reduce total dose, and limit volatilization and drift. But a critical caution applies. Nanoparticles engineered to be lethal to target pests can also disrupt soil bacteria and mycorrhizal fungi organisms that drive nutrient cycling and support plant health. The same properties that make nanopesticides effective create risk profiles that have not yet been fully characterized for tropical agricultural soils. Nanosensors represent the precision agriculture frontier. Optical nanosensors can detect soil nitrogen, phosphorus, and potassium levels in real time. Quantum dot-based plant biosensors can signal water stress before visible wilting, enabling more responsive, less wasteful irrigation management. In food packaging, nanosilver and nanozinc oxide coatings extend shelf life without chemical preservatives. The regulatory concern is nanoparticle migration into food under acidic or high-temperature conditions. Standards for this are still being developed globally, and the Philippines has no specific framework in place. In 2004, the Royal Society and Royal Academy of Engineering stated plainly, "The same properties that make nanomaterials so attractive are exactly what make their toxicological profile so unpredictable." That sentence has not lost its relevance. Nanoparticles can cross biological barriers that block most conventional chemicals: the blood-brain barrier, cell membranes, the placental barrier. This is therapeutically exploitable, but it also means unintended systemic exposure is possible in ways that larger particles would not permit. Aerosolized nanoparticles, nanosilver, titanium dioxide, carbon nanotubes deposit in the deepest regions of lung tissue. Animal studies have shown that carbon nanotube fibers can persist in lung tissue in patterns similar to asbestos A finding, with serious implications for workers in nanomanufacturing environments. In the environment, engineered nanomaterials resist biodegradation and bioaccumulate in food webs. Nanosilver present in consumer textiles, coatings, and water filters is toxic to aquatic bacteria and algae at low concentrations, disrupting the ecological nitrogen cycling that aquatic ecosystems depend on. The long-term fate of these materials in Philippine coastal and freshwater systems has not been adequately studied. The regulatory gap compounds everything else. Current chemical regulations reach in the EU, DENR guidelines in the Philippines classify substances by chemical composition, not particle size. A nanoform of a compound that is classified as safe at bulk scale may behave entirely differently, but existing frameworks do not require it to be reevaluated. This is not a minor technical oversight. It is a structural gap in the governance of a technology already in commercial circulation. Nanotechnology presents genuine opportunities and serious challenges. Holding both simultaneously without collapsing into either uncritical enthusiasm or reflexive alarm is precisely what SDS analysis is designed to support. On the opportunity side, targeted drug delivery reduces toxicity and improves therapeutic precision. Nanodiagnostics detect disease earlier and at lower cost. Nanofertilizers and nanopesticides can reduce agriculture's environmental footprint. Nano-enabled energy technologies contribute to decarbonization. Nanomembranes offer viable water treatment options in resource-limited settings where conventional infrastructure is absent or inadequate. On the challenge side, the long-term health effects of engineered nanomaterials on workers, consumers, and ecosystems remain insufficiently characterized. Regulatory frameworks have not kept pace with commercialization, and nano-specific safety standards are absent in most jurisdictions. The benefits of nanomedicine are heavily concentrated in high-income countries, while occupational risks concentrate in lower-wage manufacturing settings. Environmental persistence and bioaccumulation in soil, water, and food webs pose unresolved ecological risks. And nanosensors embedded in consumer products and public infrastructure raise legitimate concerns about covert surveillance. The asymmetry in this list benefits distributed broadly in concept. Risks concentrated in practice is not accidental. It reflects structural patterns in how technology development and its externalities are organized globally. The governance of nanotechnology is not a soft problem appended to the real work of science. It is technically demanding in its own right. A useful framework is the area approach developed by UK research councils: anticipate, reflect, engage, act. The core principle is that societal and ethical assessment must proceed alongside technical development, not after harmful applications have been deployed and the damage has become legible. The international regulatory landscape shows uneven progress. The European Union requires nanomaterial registration under REACH. The WHO has issued guidance on engineered nanoparticles in food and medicine. The OECD has developed harmonized nanosafety testing guidelines. The Philippines, as of 2024, has no nano-specific regulations from dust or the FDA. This is not a neutral absence, it is a policy gap, with direct consequences for Filipino workers and consumers. On occupational safety, workers in nanomanufacturing face the highest exposure concentrations and the least regulatory protection. The U.S. NIOSH has established recommended exposure limits for carbon nanotubes and nanotitanium dioxide. The Philippine Dole and OSH Center have issued no equivalent standards. Workers exposed daily to these materials in electronics assembly and industrial coating operations have no enforceable protection benchmark. On labeling, the EU has required disclosure of nanoingredients in cosmetics and food since 2013. The U.S. FDA has no mandatory nano-labeling requirement. Philippine FDA policy largely follows U.S. FDA precedent, leaving Filipino consumers without systematic information about the nano content of products they purchase and use. At this point, the analysis shifts from what nanotechnology does to who controls it, who benefits from it, and who bears its costs. The first question is funding. Nanotech R&D is overwhelmingly concentrated in United States, the European Union, China, Japan, and South Korea. The Philippines, like most developing nations, is primarily a consumer of nanoproducts rather than a producer of nanoknowledge. This is not simply a matter of resources. It determines which problems get researched, which applications get prioritized, and whose communities are treated as markets rather than as sites of locally relevant scientific inquiry. The second question is risk distribution. The benefits of nanotechnology, improved pharmaceuticals, better electronics, cleaner energy flow predominantly toward higher-income consumers and economies. Occupational risks, however, concentrate among workers in low-wage manufacturing environments, electronics assemblers, textile coaters, and industrial workers who are exposed to engineered nanoparticles daily, often without adequate monitoring or protection. The third question is discourse. Early nanotech debates oscillated between utopian visions, Feynman's atom-by-atom machines, Drexler's molecular assemblers, and dystopian counternarratives, including the gray goo scenario. SDS research consistently shows that both hype and fear are shaped by media framing, funding incentives, and institutional interests, often well before any evidence is available to evaluate. The fourth question is local relevance. Philippine nanotech research does exist at UP, at dust agencies, and at institutions where work on nanocomposites and agri-applications is ongoing. The SDS question is whether these research agendas are driven by local problems and priorities, or whether they are primarily replicating directions set by institutions in countries whose agricultural systems, ecosystems, and policy environments are fundamentally different from ours. 3 scenarios. Each one involves a decision that nanotechnology has already placed in front of ordinary people, not in some distant future, but now. Scenario A. The sunscreen you use likely contains nanozinc oxide particles that provide more effective UV protection than conventional formulations. There is evidence these particles can be absorbed through skin. Knowing this, would you keep using it? On what basis would you decide? Scenario B. A nano-fertilizer product promises 35% better crop yield and 40% less nitrogen runoff. Long-term effects on soil microbiome are unknown. Should a smallholder farmer in Ilocos Norte adopt it? What conditions, regulatory, economic, ecological, would need to be in place for adoption to be responsible? Scenario C. A nanodrug cures a previously untreatable cancer. It costs $200,000 per dose and is unavailable in Philippine public hospitals. Who is this technology actually serving? What does its existence mean for health equity in a country where the average household income cannot sustain that cost in a lifetime? Choose one scenario. What specific S&T intervention or governance measure would you propose, and who must be present when that decision is made? One of the clearest indicators that nanotechnology is not a niche field is how thoroughly it intersects with every other major technological and social issue examined in this course. Urbanization, nano-coated building materials, nano-enabled water treatment, and smart city sensor networks are already embedded in urban planning frameworks and infrastructure procurement decisions. The information age, the transistors in modern chips operate at nanoscale dimensions. Without nanoscale engineering, the processing power that drives the digital economy would not exist. Quantum dots are in the display panels of high-resolution screens. DNA nanostructures are being studied as data storage media. Climate change, perovskite and quantum dot solar cells are pushing photovoltaic efficiency beyond silicon's theoretical ceiling. Nano-enhanced lithium-sulfur batteries offer energy densities that could make grid-scale renewable storage viable. Nanocatalysts are improving hydrogen fuel cell performance. Biodiversity. Environmental DNA sensing, using nanobiosensors, allows species detection from water samples without physical trapping, a significant advance for biodiversity monitoring in complex ecosystems. Properly designed nanopesticides can reduce collateral mortality among non-target insects, including pollinators. Gene therapy. Lipid nanoparticles are not a tool in mRNA and RNA therapy, they are the mechanism without which these therapies cannot function. The two fields are structurally inseparable. Nanotechnology is not adjacent to the gene therapy revolution, it is what makes it possible. The Royal Society's 2004 report on nanotechnology contains a statement that has not become less relevant with time. The properties that make nanotechnology so powerful are precisely those that make oversight so urgent. The choice is not merely technical. Nanotechnology is already here in the sunscreen on your skin, in the display of your phone, in the vaccine that has been administered to hundreds of millions of people globally. The science advanced rapidly. The governance did not follow at the same pace. That gap between what the technology can do and what frameworks exist to ensure it is done responsibly, equitably, and with adequate understanding of consequence is the defining SDS challenge of the nano era. It will not be resolved by scientists alone. It requires the participation of policymakers, communities, ethicists, and citizens who understand enough about the technology to ask the right questions, and enough about power to know who needs to be in the room when the answers are decided.